To the new center. As you know, I'm a big fan of interdisciplinary work, and the most important thing is that you talk with each other, just exchange the meaning of the concepts. And I'm sure this is also a major point of, in this conference, because the same terms are usually used in different meanings, in different ways, in different disciplines. And that's where the fine-grained work, but also the exciting work starts. So thank you very much, and good luck with everything. My main talk is about trying to make sense of consciousness, brain, and I basically go just right ahead in the main 4 hypotheses or arguments. You see already hypotheses in empirical sciences, arguments are in philosophy. I have to talk louder. Okay, good. And so it's basically 4 main claims I'm trying to convey here. First, we require a particular model of brain to account for mental features like consciousness. So the neuroscientist might be puzzled. Why does this neuroscientist from Canada come about and speaks about a model of brain? It's clear, but you will see there are different models of brain, and it's not as evident which one is really appropriate. So that's more sort of an exercise in philosophy of science. Second claim becomes more empirical. We have a certain model of consciousness, and I propose here, this is a work in progress, a temporo-spatial model of consciousness, which is not contradictory but complementary to cognitive or informational models of consciousness. I will point that out. Third, and that's probably the core of my talk, because that's really the intersection where neuroscience and philosophy clash. The temporo-spatial dynamics provides a common currency of neuronal mental features, and probably the formulation already looks strange to you, because usually you're used, what is the difference between brain and mind? I try to go the other way around, that the mind is not as special and distinct as, for instance, can be traced to Descartes, but I rather look for the commonalities. And that's what I find in temporo-spatial dynamics. And last not least, if I have time, because and then in that third part, I will also present a lot of empirical data, also in the second. The fourth claim is philosophically, basically the philosophical implication, very briefly sketched. That I try to develop a spatial-temporal ontology, and that basically renders possible to replace the mind-body problem by the world-brain problem. That basically refers to the book she mentions, The Spontaneous Brain, From the Mind-Body to the World-Brain Problem, which is a real philosophical academic book. So let me start with the first claim. And this is something very much to my heart, because in neuroscience, in the empirical science, you look for very elegant designs, you look for measures, you look for paradigms, but you never really, hardly ever questions your presuppositions / the models with which you operate. And I think that's a crucial claim in philosophy. So basically, this goes back, there's a whole discussion alone, whole line of field in philosophy of science, which deals with models, and science is a very well-developed line of discussion. Nancy Cartwright, for instance, one of them. And I don't want to go into that, but I just briefly want to say 2 alternative models of the brain. So here in this model, the brain is purely mechanical, purely linear. It's like a car, meaning, and you see I put in a Toyota here, the speed of the car is directly proportional, more or less, to the degree of gas pedal push. The more you push, the faster the car. So the brain, the car in that sense, is purely linear, mechanical, and doesn't obey the rules of a critical system. And that's basically really the way we often presuppose and conceive the brain in neuroscience. So here on the left, you see in the middle the brain, and we probe the brain with external stimuli, like here's the Colosseum of Rome. And then on the right, you see this little bar thing there. That's basically the stimulus-induced or task-evoked activity. And what is important is that we assume that this stimulus on the left is sufficient for the task-evoked activity on the right. So we assume that we can thoroughly and sufficiently, the emphasis is here on sufficient, explain that task-evoked activity by the stimulus. And then, of course, if there's a sufficient relationship between the stimulus and the task-evoked activity, of course, you're asking yourself, where on earth does consciousness and self come from? Because they do not come from the stimulus itself. So they must be somewhat added by the brain. But if you have that model, if you say the neuronal activity, the output on the right is sufficiently explained by the stimulus, of course, then you are forced to consider consciousness, sense of self, other mental features as an add-on. And that's, if you want to trace it back, is a very Cartesian model of the brain. However, let's say the brain is not like a car. So imagine you walk out of here and your motorbike or your bicycle or your car spontaneously moves around. We're not yet in the age of self-driving cars or self-moving cars. So, and you observe your bicycle, you say, this is crazy, I'm a psychiatrist after all. So then you see certain spatial-temporal trajectories in which your bike moves, certain patterns, certain spatial-temporal patterns. And they look completely chaotic to you, but there's a certain system to it. There's a certain structure and organization to it. And there's certain spatial-temporal patterns, spatial-temporal organization, structure to it. And that's exactly is another model of the brain, which also goes back to the beginning of the 20th century, where you have continuously spontaneous activity. So independent of whether your brain receives external stimuli or not, your brain is continuously active. Even in sleep, it's continuously active. Only when this activity ceases, that's bad news, because then you slip into coma. So, and with that spontaneous activity indicated here by the orange lines, you approach the stimulus. Meaning your task-evoked activity there on the right is a hybrid, is a mixture between the impact of the stimulus and the impact of the spontaneous activity. So, in that sense, your stimulus is no longer sufficient for the task-evoked activity, is only necessary. So, and that interaction between the resting state, the spontaneous activity, and the stimulus, you have barely understood. This is really completely new territory, because usually they are conceived sort of in a different way. So now the question is, what does this spontaneous activity consist of? So here, it's continuously active. They fluctuates in different frequencies. You can see this here, different frequency ranges, and you will see a lot from my talk. Here, for instance, in the infra-slow frequency range, 0.01 hertz to 1 hertz, then you have different frequencies which you can measure in EEG. And basically what the brain does, it constructs its own inner time and space. So here you see already an allusion to Kant. Kant, in the Transcendental Aesthetics of his critique of pure reason, he distinguished between inner time and outer time, inner space, outer space. He put it more into a phenomenological way, but here I would argue you can put it also into a neuronal context. Yeah? So, and it's an issue, and that's the way, when I speak here of time and space in this talk, I mean this construction of time and space. I do not mean the perception and cognition of time and space. I do not mean the neuronal correlates of the perception of time and space, because you perceive time and space in terms of discrete points in time and space. I mean the active construction. And I will show you some of those construction mechanisms, how they are relevant for mental features. Here, from the spatial side, you see certain architectures, you see certain models. In philosophy, often a module-type organization has been assumed, but there are more advanced models these days, small world networks, just that the brain also constructs its own inner space. So the question then is, which model of the brain shall we use? The first one, where the brain is purely mechanical, where the stimulus is sufficient for the activity, or the second one. So, and of course, as you already saw, from my point of view, I prefer the second one. And this is very interesting when you see these models of the brain. Your brain is neither fully passive. So it's not just receiving external stimuli and processing them. But the brain can impact the external stimuli. So it's not like a Humean or Lockean-like model. So Hume and Locke assumed certain models of mind, and basically similar features we can see in our current models of brain. So it's not that far-fetched. However, the brain is also not always fully active, so it's not completely spontaneous. And that goes back, that model of mind, pure spontaneity, goes back to Kant in response to Hume. So now we can see similar things in the brain, and we currently do not know what the spontaneous activity in the brain is good for. We just don't. So maybe both are wrong. Both capture something right, but both also are somewhere. It's neither fully active, it's not 100% active, spontaneous, is not fully passive, pure reception. That's why I sort of develop in my book sort of a spectrum model of brain. You see it as a continuum between pure spontaneous and pure stimulus-induced activity. Your stimulus-induced activity is a hybrid between spontaneous and stimulus effects. However, your spontaneous activity also encodes the previous patterns of the task-evoked activity. That has been shown. So meaning your spontaneous activity is not as purely internal and not as purely spontaneous as in its name. So it's really probably that you have a spectrum model and you always more sort of the healthy brain is more sort of in the middle. And that really suggests that you really need to study empirically the interaction between the spontaneous activity and the task-evoked activity. And we coined this already in an earlier paper in Trends in Neuroscience, rest-stimulus interaction, and now we have followed up that there's a certain nonlinear interaction between task-evoked and resting state, and probably this nonlinearity is central for associating mental features. So you see, out of this very abstract model of brain, which model is valid, you can draw a lot of linkages to models of mind and philosophy. And on the other hand, a very concrete research program arises out of this, meaning rest-stimulus interaction, which is a new field because usually the two resting state and spontaneous activity were just assumed to be superimposed purely additive. But that's probably not the case. It's a non-additive. We showed this in the paper in 2017, and more will come. So you see there's a link to philosophy, and there's a strong link also to new exciting questions in neuroscience. So that was the model of brain, of course in a very abbreviated form. So now I say, okay, what does this imply for the model of consciousness? So I characterized the brain in terms of spatial temporal features, and that will become more clear throughout my talk, by inner time and space, by the construction of its own inner time and space in a dynamic way. So this is very important. I do not mean the time and space you test when you perceive or cognize time and space. But how the brain's spontaneous activity constructs its time and space, within which then the single stimuli are embedded. So here again, you already saw that figure. But now I want to point out it's not just that these different frequencies stand side by side, but there's a certain order or structure to it. Meaning, and that when you can learn this from engineering and physics, when you go into the very slow frequencies, they have a lot of power. Here, what you measure in fMRI, the infraslow frequency range, is very powerful. Whereas the faster frequencies, like gamma 40 hertz upwards, is less powerful. So imagine when you go to the seaside here, you see many small waves, less powerful, you're not threatened by them, and they will occur very often. They're fast frequency, the small, less powerful waves. However, then there are some really big waves, and there you're really scared of those waves. They're rare, but you might be very scared, or unless you're a surfer, you love those big waves. And they smash you away because they are so powerful. Same in the brain. So you have much more power in the slower frequencies than in the faster frequencies. So here you see already there's a certain structure. It's a certain organization. And this just doesn't hold for the brain, it holds for throughout nature. So it's a basic ontological principle, if you want to say so. And that can be described by the term nestedness. So basically, the smaller waves, fast frequency, less powerful, are nested or contained within the larger, bigger ones. And I have to go back here. And the typical example for that are the famous Russian dolls. You see the big one in the outside, and then you open and you see a smaller one, you open a next smaller one and smaller one. So the same with the frequencies. So there's a certain, as we say, temporal nestedness with the the faster frequencies, less powerful, being nested and contained within the next larger, faster, and more powerful one, and so on. And you have the same in China, a crystal ball, much more delicate than the Russian dolls. Don't tell the Russians that I said that, and I'm sure you have something similar here in Japan. Look, you have different crystal balls within the thing, and that's a typical example of nestedness. Yeah, I assume that you have similar things in Japan, but I didn't find anything when I Googled. Yeah, so that's basically how these different frequencies are nested within each other. So, what do I mean by such nestedness? So obviously a spatial temple, you have different spatial sizes, small to large, or different temporal durations, short to long. Then, despite their differences in the scale, they still have the same shape. The shape of the crystal balls, the shape of the Russian dolls is the same. So there's a self-similarity in shape, form, or structure. You call this scale-free properties or scale invariant because the same shape holds across different time and space scales. So now, of course, the question is, and here you can see this, for instance, what do we do in the brain? So here in the left, you see, upper left, you see the spontaneous activity as recorded, for instance, in fMRI or EEG. And you see there's absolutely, this just looks chaotic, there's no structure. However, when you decompose that signal with different techniques like fast Fourier or wavelet transform and others, then you see that there's a certain structure in the signal. And that's what you get out of here. You see the plot, for instance, on the x-axis, the frequency. On the y-axis, you plot the power. And here we do the double logarithm. And then you can see the slower frequencies have much more power than the faster frequencies. And you can see that gives the certain curves, and that's what we call scale-free or power law distribution. And you can also see that the different time points, you can see this here in the temporal autocorrelation, the closer the time points to each other, the more they correlate each other. And that's what you can see here. There's a temporal autocorrelation. And you can measure that with the autocorrelation window. So now you might ask, why on earth do we have to go through all these measures? And I'm not interested in this. Why? First, they described time-space dynamics, temporal dynamics. And second, I will show you data that they are highly relevant for mental features. So that supports my view that your time construction, the way the brain constructs its own time, that structure and organization, you see these are terms can be traced back to Kant, are central for mental features. And that's what I want to show you now. I show you here first study, and I will bring more examples of that throughout my talk now. Here it's a study conducted by one of my students in China, Jianfeng Zhang. So we investigated here anesthesia, the same subjects in anesthetic state and without anesthetic. We did an fMRI scan here. And the first thing you can see, we just compared the anesthetic state versus the awake state. You see the colorful one is the awake state, and the blue one is the anesthetic state. And you can see a clear difference in the power spectrum. So here we measured the power spectrum in these subjects. Clear difference in the power law exponents. This is the shape of the power spectrum. Remember, that's basically what we measure here. We basically measure the shape here, lower left, this shape of the curve you can measure with what is called the power law exponent. And should I keep? Okay, you're done. Okay. Yeah, and here you can see there's a huge difference between the anesthetic and the awake state. And the lower C, you see the difference between the two pictures. So they're highly significant difference. And what happens in these patients now, when you look at the power spectrum, this is very interesting. This is what you see here. So here you see on the x-axis the frequency, on the y-axis the power, and you see the brown line is the awake state, and the blue line is the healthy state, is the anesthetic state. You see, so there's a huge discrepancy in the power, particularly in the slow frequency. So the strong, powerful, slow frequencies are completely reduced in their power in this state. Yeah? So you lose, and this is important, that's the point of this paper, you lose the shape of your power spectrum. You lose this nested structure between slow and fast frequency. That's why you lose consciousness. So your temporal structure in your brain is no longer preserved. And that's why we assume, and you see here inserted many more analyses to prove that point in that paper. Yeah, but you can see it here quite nicely. So these and many other findings let us assume that maybe consciousness, and as I said, I will present more examples, is really maybe has a temporal spatial basis. So by temporal spatial basis, I mean, again, not the way we perceive things in the world, but how the brain constructs its own time and space. Yeah? Let's look at a river. When you have a lot of wind, there's a lot of its own time. As you have streams, faster, slower. That's what we mean by look at the seaside, that example. So, and we postulated different mechanisms. One of the mechanisms I just showed you, that maybe the level or the state of consciousness is related to temporal nestedness, and which you can measure, among others, with the power law exponent. You can see, when you look into that paper, you can see much more details than I can present here. So, and that's basically mean here temporal spatial nestedness. Then we have other mechanisms which we point out that also, and this is ontologically important, I will not put a strong emphasis in this talk on it, but that the brain itself, when compared to the rest of the world, has a very limited frequency range. For instance, we cannot capture the very, very slow frequency range of seismic earth waves, or we cannot capture the ultrasonar waves of the bad, philosophers Thomas and Hegel. Yeah, so because our biophysical properties of the brain are not designed for that. However, our brain with its frequency range is also nested within the larger frequency range of the world. So that's ontologically, I will later develop a spatial temporal ontology, which is important for that. So you see, it also provides the link from the empirical to the ontological. That goes with Bergson also. Yeah, so, yeah, very briefly, so you might say, so we have a view that consciousness and other mental features like sense of self, data I will present, and psychiatric disorders, later data, are really temporal spatial in their nature. However, that does not exclude that maybe that time-space dynamics also carries certain information. But it must not necessarily so. You can have time-space dynamics, for instance, completely chaotic, where there's no information, completely random. You have a time-space dynamics, but it doesn't carry completely random, it doesn't carry any information anymore. So meaning, this is not, philosophically speaking, there's not a necessary relationship between time-space dynamics and information. I would say that information and information integration, as emphasized in the IIT, is one specific subset of the whole range of possible time-space dynamics. Yeah? So we're currently trying to test that we apply our time-space measures, like scale-free activity, power law exponent, autocorrelation window, and see whether we can predict the kind of measures the IIT use, like perturbational complexity index, lived sample complexity. So maybe we can discuss this after your talk also. So then yet another approach, so the IIT pursues an explicitly informational approach to consciousness. The global neuronal workspace theory has a cognitive approach. So it's basically you need to have access to all the cognitive function, and that makes possible consciousness. And again, we would say, and this will become more clear also later in my talk, that the cognitive functions might have a temporal spatial underpinning. So they might have a certain temporal spatial organization. And I don't need to tell you, for the philosophers, this is a very Kantian-like model of the brain. You have a temporal spatial organization, and that in turn strongly shapes what and what not you can cognize in the world. So I will come back to that. So meaning the temporal spatial theory is not exclusive, it's not contradictory to it, but tries to provide a broader framework. And again, we have data where we show that our dynamic measures predict the global neuronal workspace measures like the P3B, the dorsolateral prefrontal cortex, and so on and so on. Yeah. So this is what I want to emphasize. It is not a competition between the theories. It's an integration, a larger framework. And for the philosophers of science, what I'm doing here is nothing special. Basically, I just provide a larger framework within which I integrate the current frameworks as specific instances or more limited, which can explain a number of cases, but maybe not the whole phenomenon. Yeah? So that is very important. So that's what I try to indicate here. So now I'm ready to come to my third claim. And here, now I will present you more empirical data. So the main claim is really now here. I showed you that the brain has a temporal space organization. I suggested a temporal spatial model of consciousness. So then the question is, maybe the time-space dynamics is shared between brain and consciousness. And that sharing makes possible the transformation of neuronal into mental activity. Yeah, so that's basically now, and we speak in a recent paper, which I will now elaborate a little bit on, of a common currency of neuronal and mental features. And now again, particularly for the philosophers, but also for the neurosciences and for the AI community, what I'm not looking for, I do not look for what mental states are different from neuronal states. I do not have this assumption of specialness, of distinctiveness of mental states. That's a very Cartesian model. The mind is different from the body, and we transferred that to the brain and say there's a special mechanism, a special, remember what I said initially, add on in the brain, like integration, like access, global neuronal workspace, which makes possible consciousness. I go the other way direction, say, what do they share? Maybe that makes it possible to transform neuronal into mental activity. So this is huge philosophical implication, because it's really the complete departure from the Cartesian model. Yeah? And Bennett Tucker were right in their book, Philosophical Foundations. Current neuroscience is still very Cartesian. Yeah? It's a neuronal Cartesianism that we assume a special region, a special mechanism, and add on a distinctive special add-on to account for consciousness. Yeah? So that is basically in this paper, which is published this year, and there's a lot of commentary on that in Physics and Life Review. And I want to walk you a little bit through and present data in support of this hypothesis, because that's really, for me at this point in time, really the key to look for the similarity between neuronal mental features. What and you need, in order for A to transform into B, A and B must share something. Otherwise, A cannot transform into B. Yeah? We could not communicate with each other if we wouldn't share the language, /English. I don't speak Japanese, you don't speak German. I'm originally from Germany. Yeah? So maybe some of you do, but yeah, at least I don't speak Japanese. Yeah? So we need to share something in order for me to be able to transform my ideas to you. Same here. Neuronal mental states must share something in order for neuronal activity to be transformed into mental activity. You see, ontologically, I have a completely different model here. I presuppose transformation. I do not presuppose this properties, but I will come back to that later. So, question. How can neuronal activity transform into mental activity? What do I mean by transform? Living in Canada, you're exposed to the seasons considerably, probably even more than here in Sapporo. Typical ice transforms into water, water transforms into vapor. That's sort of the background assumption when I speak of neuromental transformation. And I assume that that common currency is provided by the construction of time and space. Yeah? So that's what I mean, the dynamic construction principles like the nestedness. So now, how can I support that empirically? Now I will show you two empirical examples supporting that claim. So now I go into the hardcore empirical stuff. The first example is of the common currency is the self and temple integration. What do I mean by self? When you look into the mirror, you usually see yourself, or you recognize, and you do not only recognize yourself, you feel that you are yourself. Why? Because as a psychiatrist, I know very well that you can look into your mirror and you don't see yourself anymore, and you don't feel that you are yourself. Yeah? So I encountered several Jesuses in China, actually Mao, in Germany, Jesuses, also Nofretete, so it's also the cultural dependence. Yeah? So something can go wrong. It's very important. So there was a lot of research on the self stuff done in different domains. We did a meta-analysis 2006, and particularly here these regions in the middle of the brain, we coined them cortical midline structures, came out. And then, to our surprise, that we observed a strong overlap between the spontaneous activity and the self-related activity. Meaning between task-evoked activity induced by self-referential stimuli like your own face and the ongoing spontaneous activity. So that was a major finding for me, and it has been confirmed since by others and by us, because maybe that yourself is not a higher order cognitive representational function, as it can be again traced to some philosophical conception, but maybe it's a very basic, already present and constructed, ongoing, continuously in your spontaneous activity. And then, of course, the question, so you have a shift in your concept of self from a higher order notion, which is very prevalent even in current neuroscience, to a very basic fundamental notions which might actually precede and lie at the bottom of any subsequent cognitive functions. So then we said, what does this overlap between spontaneous activity and self-related activity consist in? So again, you already have seen this slide many times, you have seen this time. So the assumption is maybe it's this time-space dynamics of the spontaneous activity which encodes information about yourself, your sense of self, your self-relatedness. And that's exactly what another postdoc of mine from China, Zirui Huang, tested, and actually also with a student from Japan. They did that together. They basically said maybe your spontaneous activity measured as a resting state in fMRI, the temporal structure, like the power law exponent, is related to the sense of self. So how did we test that? First, we measured subjects in fMRI in the pure resting state without any external task. And then we applied a self-consciousness scale, which measures distinct aspects of self, private, public, and social. And of course, the hypothesis was if there's really a sort of a spatial temporal encoding of your sense of self, maybe your temporal features in the resting state without applying any self-specific stimuli sort of predicts your self-consciousness. First thing. So here you see these curves, the power spectra in fMRI. You can see this in the typical midline regions, medial prefrontal cortex, posterior cingulate cortex. X-axis is the frequency, Y is the power. And you can see again, this is the frequency range of fMRI, 0.01 Hertz to 0.1. And you see, again, the slow frequencies have a lot of power. The faster frequencies have less power. So remember my example from the seaside, where you have the slow waves are very powerful. And each trace is one subject. So you see the huge inter-individual differences in the detailed shape of these curves. And this is not a noise artifact. This is real. Yeah? So this is intrinsic inter-subject variability, which makes sense. We're all different. And also you see some differences between the two regions. So now the question is, do these curves predict the respective subject's self-consciousness? And that's exactly what you can see here in this one. You see here on the left, here in the private self-consciousness, on the x-axis, the power law exponent, your shape of the spectrum, meaning the higher your power law exponent, the more power in the slow frequencies, the higher your private self-consciousness. So this was published 2016. That was at the time for me a really eye-opener. Maybe there's indeed a temporal encoding in the spontaneous activity of yourself. Then we replicated the same thing in EEG, faster frequency range, published this year. Here's a power spectrum, the different curves, individual subject. And again, you can see here for the private self-consciousness, here on the x-axis, power law exponent in EEG. And again, the more slow frequencies, the higher your self-consciousness. So meaning maybe your self-consciousness is strongly based on the strong, powerful, slow waves, which are somewhat temporally much more stable than the faster waves. Yeah, and the more stable, and they give you a certain self-continuity. There's a certain self-continuity in there. I want to come back to that later. So maybe, and these waves are here, you can see this. We did also other measures for the experts, autocorrelation window and cross-frequency coupling in EEG. All three power law, correlation window, cross-frequency predicted the sense of self. And they all sort of have a temporal integration. Maybe they account for the integrative function of self, that you can integrate different stimuli. Then spatial temporal integration would be sort of a common currency between the neuronal and the psychological level. And now we're currently following up that with other experiments. So the idea then is here, each of these measures, power law exponent, autocorrelation window, modulation index is a cross-frequency coupling, encodes, measures a slightly distinct aspects of temporal structure, temporal nestedness, temporal continuity, temporal integration. And these are distinct aspects of self. So you see that we try, maybe there's similarity of the temporal features on the neuronal level. There's a similar temporal structure on the neuronal level and on the psychological level. So now we are currently following up on an experiment of trying to manipulate these temporal features also on the psychological level, bringing in some delays in the task and so on and so on. Yeah, and the comparison is here. So, I'm a big fan of Leonardo da Vinci, the Renaissance painter and scientist and so on, because look at this picture. This is a very famous painting, The Last Supper in Milano, and you see, you basically have the feeling it's almost alive. Yeah, one is the one who betrays him, and of course you can guess who it is among those disciples, and you can see it's almost alive because he creates a 3D, a very dynamic painting on a 2D surface. And that's exactly what your brain does. It continuously creates sort of a virtual 3D dynamic spatial temporal construction, exactly like what you perceive here in the painting. And when you see this in all his painting, it's unbelievable. Yeah? And that's exactly what happened with the brain. So, second example of common currency. For that, I turn to psychiatry, particular to bipolar disorder. Bipolar disorder is when you have extreme mood fluctuations between depression and mania. Mania, you're abnormally happy, depression. And we investigated the neuronal variability, and we found opposite changes between sensory-motor network and default motor network, and exact opposite changes in mania and depression. But the most important one is this one, which we published last year. What we tried to do here so here we said, okay, many depressed patients, we know that their experience of time is extremely slow. Ask a severely depressed patient, nothing moves, nothing changes. Severely depressed and everything is stalled. And of course, if you do not experience any change anymore, of course you become very sad. Nothing changes. And then you have the feeling you have no future anymore. So maybe these kind of phenomenological experiences, which are well documented in depression, can be traced to an abnormal time speed in your brain. So now then the question is, how do you measure time speed in the brain? I will come back to that. So the assumption is here that maybe time speed is a common currency between the brain's time construction and your subjective experience. And that really amounts to what I would say is a neurophenomenal hypothesis. Yeah, I refrain here from phenomenological because I don't want to get into all that. So it's a more so what in depression you can see here on the x-axis you have the speed of inner time. That's your subjectively experienced time. Y-axis, inner outer time, synchronization. The more you're in sync with the outer time, let's say while you dance a tango, the more synchronized and the better you feel. Depressed patients, their inner time is too slow, so they're completely out of sync with the outer time. They're too slow. We are too fast for them. However, for the manic patient here, it's the opposite. They're too fast and we are too slow for them. Yeah? When you see a manic patient, it's very impressive because they're just way too fast. Yeah? Meaning we are too slow. So, and what is important, so then we suggest, so how can we measure that? So it is clear that the time speed experience is altered in these patients on a phenomenological subjective level. How can we measure time speed in the brain? So we did that with measuring, sorry, there was one missing here, with measuring the neuronal variability. Variability is the root mean square of the amplitude, so it basically designates the degree of change to which your neuronal activity changes. And change is time speed. If there's a lot of neuronal variability, you have a lot of change in your brain activity, meaning it's fast paced. Meaning the 3 minutes you will perceive them as 2 minutes. However, if your time speed is rather slow in your brain, you might perceive this lecture, which goes for 45 minutes or 50 minutes, as 2 hours and eternally boring. Yeah? Obviously, I don't hope that that is the case. So, however, so what we did then, the second step, so neuronal variability served as an indices of time speed on the neuronal level, supposedly corresponding to the time speed of inner and outer time in these guys. Then we looked, how do we know inner time speed perception? There's a very solid literature that is related to the somatomotor network, motor cortex, basal ganglia, dopamine. In Parkinson, it's very well known. Time speed perception. So we took the somatomotor network, neuronal variability, as a proxy for inner time speed. However, these patients experience the outer time in the opposite way. So for the depressed patients, the outer time is way too fast. So we took the visual cortex neuronal variability as a proxy of outer time speed. Yeah? And then we hypothesized they must show opposite ratios between inner and outer time speed, between neuronal variability in somatomotor network and visual network. And that's exactly what you can see here. So you see in green, the healthy subjects, neuronal variability in the two networks, relatively balanced here. Then you go to the depressed patients, you have significantly decreased neuronal variability in the somatomotor network. That means the network which mediates inner time speed perception shows too slow neuronal time speed. Neuronal variability is too low. So here you see decreased time, low time speed, slow time speed in experience, slow time speed on the neuronal level in the somatomotor network. And in the visual network, because they perceive the outer time as way too fast, you see huge increase in neuronal variability. Yeah, and you see that pattern. And in mania, where it's exactly the opposite, inner time speed is too fast, and the outer time, the time in the outer world is perceived as too slow, you see exactly the opposite pattern. Yeah? So, and we have now other findings where we could really replicate that. So that means maybe, and that's the support for this case, maybe the time speed is a common currency between neuronal level and perception or experience. Yeah, here the time speed is the common currency, and you can measure that with the neuronal variability. So now we are trying to follow up, and we are also trying to take other features like duration, which might be central in autism, where we have findings in that direction and also published. So that, from my point of view, carries major implications for neuroscience, so that we say maybe in addition to social, sensory-motor, affective, cognitive neuroscience, which are about brain function, we need to look for the underlying brain dynamics. And what we coined in this paper, spatial-temporal neuroscience. Yeah, and that we need to that's the missing link, or Victor Lamme speaks of a missing ingredient in current consciousness theories, that we miss this sandwich here, spatial-temporal neuroscience and the common currency. So then let me close with that. And of course, that spatial-temporal neuroscience is about neuromental transformation. That's what we are trying to work with the category theory, and also with now we published a paper on that. Then spatial temporality of mental features. So for me, it's extremely important to ask my patients, what is your subjective experience of time and space? Yeah. Recently, we're just starting now a study on somatoform disorder, where we say maybe these patients have abnormal constriction of their space, which is abnormally restricted subjective space. So that's the spatial temporality. So there I'm very strongly a phenomenologist, which are my philosophical roots. And then, of course, it's a dynamic view of the brain, a spatial temporal view of the brain. So briefly, I come to the fourth claim, the more philosophical implications. I can only touch briefly upon this without being able to fully develop, but you already see there was a lot of philosophical background assumption in my talk, either where I go with curtain models or where I say, no, I reject, like the Cartesian model of the specialness and distinctiveness of mind as distinguished from body, I reject, because the notion of common currency implies similarity and non-specialness of mental features. Yet another model which I really strongly rely on, after all I'm German, is the Kantian model of the organization, the structure of mind. That's what you see in my concept of spatial-temporal neuroscience. So I take a Kantian concept, take it from the logical context in which he presents it into the empirical context. So now, but after all, I'm also a strong philosopher, and I'm really interested, what I'm really after all is ontology. And this is very important now for the philosophers. And yeah, before going very briefly into that, I think the spatial-temporal dynamics is of central relevance for current artificial intelligence, because it implies that your brain has a certain spatial-temporal dynamics, and I think that is missing in current models of AI. Yeah, that's why they don't have certain capacities like aligning to the space-time features of the world, despite all progress. So I do think that on the cognitive level, they're really good, and they're already much better than us. However, they're missing this spatial-temporal level. But that's a bold claim, which I'm happy to discuss further. And we're currently doing a project with Carl Friston on exactly this, combining this time-space dynamics with this idea of free energy. So let me sketch some of the philosophical implications, where I say, now I shift from the empirical to the ontological, spatial-temporal ontology. What do I mean by that? And I try to apply it very briefly, as I said. Here, the details can be read in the Spontaneous Brain book. So here, I found this in the New Yorker. It's very nice, the mind-body problem. How can we solve this? And so, for me, very important, ontology is not just a subset of metaphysics. I know that in the analytic philosophy, usually ontology is just considered a subset of metaphysics, which I do not follow. Ontology is for me about the existence and reality in the natural world, and exactly those features that distinguish the natural world from the rest of the logical world. And of course, one of those distinctive features is what I try to indicate here with this quote from Tesla. Nikola Tesla, actually read his biography, he's a quite interesting person, is energy, frequency, and vibration. So, and you can see this is, of course, a very strong link that temporal spatial dynamics is universal. Yeah, nonlinear system, scale-free activity is not only in the brain, it's throughout nature. It's abundant. Criticality, it's so meaning there must be an ontological relevance to it. And that's what I very briefly develop now. So the traditional ontology, particularly prominent in the Western philosophy and Western world, is really what I call here element or property-based ontology. So certain elements or properties or earlier substances, mental or physical, are supposed to be the most basic features of existence and reality. Elements or property are primary, and then you can have some relation to it. You see this paradigmatic in the current mind-body discussion. You have all kinds of models, and panpsychism ultimately assumes psychic properties to be the most basic. Both monistic and dualistic theories presuppose element-based or property-based ontology. However, it's the sidelines of Western philosophy and much more prevalent in Eastern philosophy as far as I can judge. You have sort of what I call here a relation-based ontology. So relation are the basic features of existence and reality. Relation or processes, for instance, Alfred North Whitehead, are primary, elements are somewhat secondary. A person where you can see the mixture between these two is Leibniz. Yeah, he has a very dynamic relation-based view, but then he links it to the monads because he thinks he needs to make that. Yeah. So how can you describe this? Let me say element-based ontology. I try to simplify here, so please don't quote me over this. You have primacy of elements or properties, and then you have relations. In the relation-based ontology, you have first the relation, the structure, or you have a co-occurrence and the relation. So, and that's very important. In this case, applied to neuronal mental features, you would assume that you have mind and body as possible different properties or substances or mental and physical properties. And then, of course, yeah, I can make it. Thank you. And then, of course, you ask how they are related to each other. That's the mind-body problem. Meaning, the mind-body problem is a consequence, is a necessary consequence of your presupposition of a property-based ontology. However, if you assume a relation-based ontology, you say that maybe mind and body are just abstractions or consequences of more basic underlying processes of relation and structure. Then the mind-body problem as it is conceived in current Western philosophy is no longer a possibility, meaning it's nonsense. Yeah? It's not included in the logical space. Yeah? McDowell would say in the logical space of reason. I would prefer the logical space of nature, but I don't want to go into that. So, then let me give you a little bit more substance. No, I should not have said substance here, a little bit more insight into what I mean. Structural realism is one of those forms, primacy of relation. They call it ontic structural realism. You have different forms of ontic structural realism, moderate, and that's what I go with, that you have a co-occurrence of relata and relation, as distinguished from the more radical form, eliminative ontic structural realism. So now I say, look, these relations are spatio-temporal relations. Yeah, they're intrinsically dynamic, they're intrinsically temporal and spatial. Note for the philosophers, I'm just speaking about the natural world, I'm just speaking about ontology. I do not speak about the logical world as a whole and metaphysics. Very important here. So don't quote me on that. Let's just speak here purely ontology as distinguished from metaphysics. So spatial-temporal relation. And then, of course, I would argue, and now I make a very shortcut here, you have also the brain. Remember, I said that the brain, spatial-temporal, might be nested within the larger spatial-temporal structure of the world. That's then what I would say is the world-brain relation. And that is, of course, is a spatial-temporal relation because it's nested. It's like the Russian dolls. The world is the largest Russian dolls which we see from the outside, and the brain is nested within that. Yeah? So then, of course, the question is, now, if I can show that the world-brain relation and its spatial-temporal features is a necessary condition of possible mental features like consciousness. Necessary. The emphasis is here now for philosophers on the necessity. Yeah? Because that's what is currently missing, that we do not have a necessary connection between neuronal and mental states. That's why we have all this dilemma with the mind-body problem. So I call this in the MIT book the contingency problem. And as usual, Thomas Nagel, whom I appreciate really very much because he nicely exposes the problems. He doesn't offer a solution, but he exposes the problem in current philosophy of mind in particular. It appears at first blush that we have a clear and distinct enough graph on both phenomenological consciousness and physical brain processes. You see that there can be no necessary connection between them. And that's the problem. That's, for me, the core problem of the current mind-body problem and the whole debate about consciousness and philosophy. We lack this necessary connection. That's why I speak of a contingency problem. So in the way you see how he formulated, he already sort of implicitly, because you have an element-based ontology presupposed here, you basically, any necessary connection is excluded by that. Because you already presuppose in your logical space, purely conceivability, I'm talking now here, that there's a possibility that consciousness and brain might be subserved by different ontological properties, less physical and mental. Even if you later reduce the mental to the physical or physical to the mental, you still have that possibility, and that makes it impossible that you get a necessary connection. That's exactly what we're facing here. So now, I would argue that if you have sort of a different ontology / relation-based, then you can say that maybe the world-brain relation necessarily entails the capacity or possibility or predisposition, as I say, for mental features. So then you have a necessary connection. Here, the right is a beautiful quote from a beautiful, great paper, 2002. The right point of view would be one which, contrary to present conceptual possibilities, included both subjectivity and spatial-temporal structure. That's why I put it into italics. From the outside, all its description implying both these things at once, so that it could describe inner states and their functional relations to behavior and to one another from the phenomenological inside and the physiological outside simultaneously, not in parallel. And that's exactly what I say. Look, maybe the spatial-temporal structure as a common currency between neuronal and mental implies both, necessarily, when you conceive it in an ontological framework. So that basically provides a necessary curve, and I come with that basically without elaborating to the details that say ultimately you can, and please read chapters 9 to 11 if you want to know the details. It's really that the world-brain relation can have a necessary relation to mental features. And if so, if you can show that, then your mind-body problem can be replaced by the world-brain problem. Yeah, as strange as it sounds for you at first instance. And come to the end of my talk, take-home message. We require a specific model of brain, I would say a different model of brain, not a cognitive, not an informational model, but primarily a dynamic model, which then incorporates cognitive informational model. It does not stand in contradiction to it. It entails them as a specific specification of the dynamics. Second, we need a temporal spatial model of consciousness, and again, rather than primarily a cognitive, informational, or affective model. And again, it's not a contradiction. It specifies, these models specifies a temporal spatial dynamic, but the temporal spatial dynamic underlies them and their possibility of being linked to consciousness. Third, temporal spatial dynamics provides the common currency of neuronal mental features. You remember the example of self, you remember the examples of the bipolar disorder, the time. And fourth, spatial-temporal relational ontology renders possible to replace the mind-body problem by the world-brain problem. And with that, I come to the end of my talk. Thank you very much.